functions are probably one of the most important concepts in mathematics, and especially how mathematics applies to the sciences. The study of functions is what calculus is really all about, and really the interplay, as I said, between mathematics and the sciences happens via functions. So understanding functions is completely crucial to success in the sciences, the mathematical sciences, and certainly in mathematics. So what I want to do really is to go through the foundations of what functions are very slowly in general, explaining the basic idea and making sure that we're really, really comfortable with the definition of a function more than anything else. Because I think people often have quite a fuzzy feeling for what functions are. They think they're these formulas, and formulas do give functions, but you've got to understand the concept is broader than that. So I think what I'm going to do is, rather than jump into some sort of immediate definition, I'm going to give you a couple of examples which will look really different, but will actually both be examples of functions, and I'll give a good illustration of what the core abstract idea is. So let's do an instructive example, shall we? So here's an instructive example. Okay, so when we write some expression in terms of x, what do we really mean? So let's take a moment to kind of unpack this. So when we write, so let's choose an expression. Let's choose the expression, a rational expression in x squared plus 1 divided by x minus 1. What do we mean? What do we mean? So throughout everything we've done up until now, if I've written an x or any other letter, it's always represented a number. So this, as far as I'm concerned, represents a number to start off with, doesn't it, right? That's kind of the most obvious interpretation of this. Okay, x is a variable, it's a stand-in for a number. So x squared plus 1 divided by x minus 1 is some number. It'll depend on the x, but it is a number. So that's kind of the first interpretation of this. So maybe I'll call this the more elementary interpretation. In the sense that it's the one that we've been thinking about up until now. So, as I said, x represents a number. Of course, it represents a number. So this expression, so x squared plus 1 divided by x minus 1 is just a number. Very good. But there is a slightly more sophisticated way to think about this. So a little bit more sophisticated. So a more sophisticated way to look at this is, sure, this represents a number, but you see, x is a variable. X is a stand-in for a number. So it's not just one fixed number like 5, 6, or 7. It could be a variety of different things. So x is a variable number. It's a variable number. Okay, so what does that mean? So this expression isn't just some fixed number. It's a lot of potential numbers. It itself is a variable number. It can vary. So a variable number. So really, what I think we should be thinking here is the following. I mean, this x squared plus 1 divided by x minus 1, it represents, in a sense, a collection of numbers, all sharing a common form. So x squared plus 1 divided by x minus 1, it represents a collection of numbers. So it's not really just one, is it? Collection of numbers all sharing a common form. Namely, they're all of the form x squared plus 1 over x minus 1 for some number x. A common form. Okay, so let's label things a little bit. So this second approach is a little bit different, right? It's kind of interesting. So x squared plus 1 over x minus 1 is just the number, of course, if I fix some x. But you see, this is some sort of collection of numbers, really, all sharing a kind of a common pattern. So because x squared plus 1 over x minus 1 can vary, we might as well label it with another symbol. Or maybe another letter. So this can vary. So it could be a variety of different numbers. So how do we deal with situations where we don't have just one number, or we use some stand-in? So let's use a letter. So let's label it. So label it. Let's say y is equal to x squared plus 1 over x minus 1. Now, I'm only doing this just to illustrate the fact that this quantity can take multiple values. And it's kind of a succinct way of describing it. Now, this y, I could have chosen any letter at all here as well. There's nothing special about x or y. I could have chosen a and b. We often use a and b as constants, but there's no real reason to choose x and y other than the fact it's a convention that we stick to most of the time. Now, let's think about this. When I am thinking about this expression x squared plus 1 over x minus 1, the x, we're basically free to choose it. Okay, we can say, okay, let x be 5, let it be 10, let it be 7, let it be anything. We're free to choose this. So at this point, here, the x, we're going to call it something. We're going to call it the independent variable because we have kind of, it's independent how we choose it. We can choose whatever we want, really, within reason. X is called the independent variable. And it's independent because it's independent to be whatever it wants. So we can choose this, essentially. And I should say within reason here. We can't choose anything for x. So take a moment to look at this expression. There's a specific value we can't choose, namely, we can't choose a value where the denominator becomes 0. And when would that happen? It would have to be when x is not equal to 1. But I think any other value is fine. Now the thing is, when I make a choice of x, that essentially pins down a choice of y. So I think y should be called something kind of similar to this, but instead of the independent variable, we should call it the dependent variable, because it's going to depend on the value of x. Dependent variable depends on x. So this is kind of interesting. Up until now, we've been thinking about expressions with kind of variable numbers, x's, a's, b's, this kind of thing. But we've never really had a scenario where we've had two variables which kind of rely on each other. So this is kind of an interesting idea, right? We've got two variable numbers which are kind of tied together by some information, and the information essentially is the expression x squared plus 1 over x minus 1. So let's visualize this a little bit. So here's a way to kind of picture this information. So there's a visualization. It's good to have kind of lots of different ways to kind of picture mathematical concepts. It gives you deeper understanding the more ways you can see it, the more angles you can see it from. So here's a cool thing to think of this as. So I've got kind of two variables here. I've got an x and a y, if you want. And let's imagine I have on the left here, so I've got two number lines. And on the left, I'm going to represent kind of the x variable, and on the y, I'm going to represent on the right, I'm going to represent the y variable. So here's what I'm going to think. I'm going to think about kind of the left-hand side as the input, essentially, kind of like a machine. And I'm going to think about the right-hand side as kind of an output. And I imagine myself inputting a value of x, and I apply this formula, this expression, x squared plus 1 divided by x minus 1, and what happens? Well, I end up with some value y, okay? And of course we know what y is equal to. It's my x squared plus 1 divided by x minus 1. And if you want to be really concrete about it, which I think is a good plan in certain cases like this, if I took 3 here, for example, what would 3 go to? 3 would map across to, well, it would be 3 squared, is it plus 1 divided by 3 minus 1. So what's that equal to? 3 squared is 9, plus 1 is 10. 10 divided by 2, this is equal to 5. So 3 maps to 5 if you want. Okay, it moves across to 5. Okay, so this expression, x squared plus 1 over x minus 1, when viewed from this perspective, is like some sort of, it's like some sort of recipe, if you want, or a rule, which when I take an input, which I'll call x, it spits out another number, an output, which I'm going to call y. And the rule is x squared plus 1 over x minus 1 is the output if x is the input. I should say, and I've mentioned this a moment ago, but I'll say it again, we don't have complete freedom in the inputs, right? So observation. So, I mean, x squared plus 1 divided by x minus 1, it only makes sense as long as x is not equal to 1. So we've seen this before when we were doing algebra with expressions like this, and I was telling us don't just blindly do algebra. Remember, what you're dealing with represents numbers, and there may be occasions when the numbers don't work. You might be dividing by 0 in this case. So x squared plus 1 only makes sense for x not equal to 1. And this is exactly because we cannot divide by 0. It has no meaning. Okay, so let's kind of conclude everything. What do I see? So this expression, x squared, so conclusion, so x squared plus 1 divided by x minus 1 can be interpreted as a rule, like some sort of recipe if you want, some specific thing that does something, which associates to any number let's say x in, well, I can't just choose any real number, so I've got to write down the real numbers excluding minus 1. So let's write it like this. This is a bit of a cumbersome way to do it. So these are the things which are strictly less than minus 1, union 1 strictly bigger. So that's just a pretty nasty way of writing the real numbers excluding 1. So to any x in this, a unique number which I'm going to call y, which is equal to x squared plus 1 divided by x minus 1. So again, let me just label a few things. So in my mind, this is just the x. This is just real numbers where x is not equal to 1, the x is kind of like an input, and the y is kind of like an output. That's how I talked about it before. Okay, so interesting. So this rational expression, x squared plus 1 over x minus 1, for a specific value of x, yeah, it's a number, but because I can think about x as varying, I can view it from this perspective of actually being some sort of recipe or a rule which associates to any x another number. It's like an input and an output. So let me show you another example which feels extremely different, but it's actually going to be the same basic thing. So here's a second illustrative example. Or maybe instructive example. So another instructive example. Okay, so here's just something which feels completely different. So let's ask the following question. What is the temperature? The temperature, I don't know, in a room between 2 moments in time. So between, I don't know, let's say 1 p.m. and 3 p.m. Okay. So 1 p.m. and 3 p.m. Well, this just doesn't feel at all like what I've just done, right? A moment ago, I was trying to interpret this rational expression in x. This looks really, really different than the previous example. So it looks very different. To the previous example. This is a kind of a physicsy type question almost, right? It's like an actual science question. So what's it got in common? Well, let's think about what's going on here. There are 2 quantities of importance in this question. One of them is time. The time between 1 p.m. and 3 p.m. Okay, that's a quantity in this. Then there's also the quantity of temperature, the actual temperature at any given moment in time. So let's label a few things. So let's label T as, let's say this is your time. Time, say in hours after noon. Okay, so I'm saying in hours to kind of fix a scale if you want, or fix units. And then at a given moment t, that gives me some time between 1 p.m. and 3 p.m. There's going to be a time, and it's going to depend on the or there's going to be a temperature, sorry, and it's going to depend on the time. So let's label that information too. Let's write f brackets t. So this is pure notation. This isn't multiplication. F doesn't represent a number. It's just a letter I've written down to illustrate that this symbol, or this thing that I've written, is going to be the temperature. And I hate to do this because I'm British, but I'm going to do it in Fahrenheit. At time, let's say t p.m. Remember, t is in hours, so that kind of makes sense. Okay, so first of all, these are two quantities. One is a time, one is a temperature. And they're both variable, right? The time is variable. It's going to vary depending on, well, where you are between 1 p.m. and 3 p.m. So this is a variable. And so is this, right? This is just a variable number. It looks kind of scary because it's f parentheses t, but it is just a number. It's just notation. Okay? And something to say here, kind of immediately. This f of t isn't necessarily going to be given by a nice simple formula in t, is it? Right? It's not necessarily going to be the case that the temperature at time t is t squared plus 1, right? Something simple like that. We know the world is much more complicated than that, and the way the temperature is going to change over time could just do all sorts of weird and wonderful things. So there is no reason to believe that there's some slick formula for this. This is just it's just a quantity, right? So this won't necessarily be given by a neat formula. Okay, absolutely not. Okay, so what's this got in common with the previous situation? It really feels super different, but actually it's incredibly similar. So visualization. Well, what have we got? Let's draw two number lines side by side, just like we did a moment ago. And let's think about the one on the right as, or the one on the left, sorry, is representing time. And let's think about the one on the right as representing temperature. So time. There are two moments in time which are very important, 1 p.m. and 3 p.m. They're the kind of the start and finish of this story. So let's mark on the number line, let's say 1, and a point on the number line 3. Okay, so this represents 1 p.m. and this represents, of course, 3 p.m. So now if I take some t in here, at some moment in time, there's going to be a temperature in the room at that time. So there's going to be a number associated to it, namely f of t. So I can think about that as corresponding, or mapping maybe, I don't know, it's up to you how you think about this, to some value y is equal to f of t over here, just like before. And in my mind, I'm thinking about the time as, well, kind of an input. And I'm thinking about the temperature like the output in my previous case. So to any moment in time t, there is a temperature. To be really specific about it, if I was to take, I don't know, something like this position here, 2.5. Well, 2.5 corresponds to what? It would correspond to the temperature at what time? Well, at 2:30. 2:30 p.m. Okay, so that's really similar, isn't it? Right? We have two quantities related by some rule, and in this case, the rule is much more complicated than the previous one. It's talking about the way temperature changes over time in a room. But it's the same basic principle, right? We have one which is like an input, in this case the time, and the way we've set it up, the output is like the temperature. So I say the input is 2. That means the output is the temperature at time 2 p.m. So let's conclude how to kind of view this from the correct perspective. So the conclusion is the following. So how the temperature changes. So how the temperature changes between 1 p.m. and 3 p.m. This is the way I've set it up. Can be interpreted as a rule which associates to any number, let's say t, in the interval. So I can only be between 1 and 3, can't I? Because I'm only interested in the time between these two, or the temperature between these two times, the way I've set it up. A unique number, let's call it f of t. I could label it y as well, but let's just write f of t here. I know I wrote y above, but let's just write f of t. And let's just remind ourselves why, because this t is the time. Okay, and I can think about that as the input. Okay, and this f of t is the temperature at that time. And I can think about that as the output, using this kind of picture from above. So these are two really radically different things on the surface, right? The expression x squared plus 1 divided by x minus 1, that rational expression in x, and the idea of, well, what's the time in a room between 1 p.m. and 3 p.m.? They're living on different planets. But I can see that from the correct, or from a certain perspective, they actually have exactly the same form. They're the same abstraction. So these two different situations are examples of what we are going to call a function. So we've got two different situations, one common abstraction. That's a nice way to think about this. So two very different examples, maybe. One common abstraction. Abstraction is a really interesting thing because it's this ability that we have to draw parallels between seemingly very different things. I mean, just as an analogy, one that you've probably long since forgotten really, but is kind of amazing. If you take the idea of, I don't know, counting at all. Counting is an amazing form of abstraction in the sense that if I take 3 sheep and 3 stones, okay, sheep and stones are completely different things, but if I have 3 of them each, that is some common abstract idea that links these two situations. It's exactly the same thing here, right? There's this abstract underlying idea which is turning up in 2 very different ideas. So counting's the same. The number 5 is a huge abstraction. It's the abstract description of a collection of what we call 5 objects. And it could be any 5 objects. It could be 5 pencils. It could be 5 planets. They share some sort of common abstraction. It's kind of the incredible power of mathematics. Okay, so let's try to really write this abstraction down super, super carefully. So what do we have? We had some sort of rule, some situation where there's a way of assigning an output to an input. And the crucial thing is the inputs aren't completely anything, right? For example, in this case, the inputs were only allowed to be in that interval. And in this case, the inputs were only allowed to be in this kind of union of 2 intervals. So what I think is I need to have that freedom. I can't just have a situation where I can have any input. I need to kind of have a bit of restriction. So here we go. A function. A function. I'm going to label it something. The word function starts with F, so let's call it F. We could use any letter or any symbol, really. With domain D. So this is part of the information of the function. So with domain D, so this is if I go anywhere, this is a subset of the real numbers. So in the above examples, the domain is going to be, this is the first one, this is the second one. So essentially what the domain is going to be the allowable inputs. But that's me not get ahead of myself. So a function f with domain D is a rule which assigns or associates, it's up to you, to every x in D exactly one. This is important. Only one real number denoted, so I'm going to use some notation, denoted f brackets x. So maybe just say a few more things. The subset of all possible, so the way I'm going to think about this is I'm going to think about the x kind of as the input here. It's like a machine. You're feeding something into it, you're getting something out. When I was first taught this, my teacher kept on going on about sausage machines. He always talked about the fact that you feed in meat and you get sausages out. I'm like, okay, do I understand what he's talking about? But the principle is there, right? You take an input and you get an output. So the function is kind of the rule. It's the machine, right? So exactly one real number denoted f of x. The visualization for this is the following. So the way you should be thinking about this is exactly as we've just done. I've got my inputs over here on the left, my outputs on the right. And if I choose a point x on this side, which is in the domain, it's got to be in D. D are the allowable inputs. Okay, so you can't, the D is part of the information of f if you want, right? It's part of the data of the function. So the only possible inputs are in the domain. So these are the allowable inputs. So all allowable inputs. All allowable inputs. So the visualization is exactly as we had before. I think about the information of the function as being like a machine which sends x over to, I'll write f of x here. And you could use y is equal to f of x if you want to be succinct, but there's no real need. So this is your input. And this is your output. This is your output. So just a couple of things to be really aware of here. In fact, maybe before I do that, I'll just give you one extra little bit of definition. The possible outputs. So the possible inputs are called the domain. The possible outputs are called the range. So the collection or the subset, I'll just say collection, it's a bit less fancy. The collection of all possible outputs is called the range. It's called the range of f. If you want to use a stupid analogy, I mean, if you were to talk about the range of a rocket, right, some sort of ballistic missile, it's how far it can travel, right, in theory. Well, using this kind of picture, you got the same story, because you'd be firing off from different positions. The range is everywhere that you can land on this side. So that's the reason it's called range, really. But really, it's all the possible outputs. This is just a subset of the real numbers, right? It's some collection. It could be the whole real numbers. It could be everything. Everything could get hit, but it's not guaranteed. Okay, so the last thing I want to do... No, I think this is a good place to stop to begin with. So this is an incredibly important definition. A function is a rule which associates to any number in its domain. So the function is kind of two things, really. It's a choice of domain and a rule that associates any point in that domain some other number, and exactly one number. So we'll look at this in the next video. Exactly one's important. You can't have two outputs. But let's stop there for a moment.